In the earliest 20th century, all right, they thought that electrons maybe were traveling around the nucleus in an orbit, all right, kind of like planets around the sun. Now, in this little picture, the red dots are electrons, the little purple dot and the plus in the middle, that's the nucleus. If this was correct, then any orbit should be possible. So depending on the energy. So if you wanted to have the electron super close to the atom, that should be possible. If you wanted to have the electron way out here, that should be possible. As long as the energy wasn't a problem, you should be good to go. All right. But interestingly enough, electrons moving around positive protons create a little bit of electric energy, all right? And that electric energy is kind of like friction. And if you let the electron go around and around and around and around enough, it's going to create quite a charge. And eventually it's going to have to emit that energy out as like a burst, all right? Maybe a burst of energy. Who knows what it's going to be. But you can't have negative electrons circling positive protons and not expect to have some energy problems. So if the atom was going to do this, according to classical physics, at the end, the atom would just explode or implode, or it would break down, whatever you want to have it. And that's bad for us because atoms are in our bodies, all right? And fortunately, most of the time, our bodies are okay. The atoms don't start breaking down all of a sudden. So what this means here is that classical physics really didn't understand how the atom was put together, all right? Classical physics really didn't have the answers to how electrons can stay in stable quote-unquote orbits around the nucleus. So Bohr came in and said, well, throw classical physics right out the window. It's wrong. And he said, we need a new theory. And he said, let's use a quantum or wave mechanics. So arguably, Bohr was one of the first ones to use the idea of quantum mechanics, which was kind of interesting. He based it, by the way, on Einstein's ideas, apparently, of the wave-particle duality, and he just applied it to atoms. Now, Bohr assumed that electrons can only exist in certain orbits around the nucleus, and he called them stationary states. So I'm going to draw a little atom here in the upper left-hand corner. In the middle is the nucleus, and this right here is the electron. And let's say that that's an allowed state, and maybe this one is an allowed state. But if you wanted to have an electron in this dotted one right here, no, said Bohr. You can only have certain stationary states where electrons can be. It can be in the closer one or the farther one, but it can't be in the middle. It can't be closer to the nucleus. Maybe it can't be out there. This was very revolutionary because no one had thought, well, there would only be certain orbits that are possible. And it kind of doesn't make any sense at first because, yeah, electrons, as long as it's not a problem with energy, should be anywhere from the nucleus. But that's not what people see now. Electrons are restricted to quantized energy states. Here's that quanta term again. Quantized energy states are just the allowed energies possible between the nucleus and the electrons. And you can't get in between the quantized energy states. You have to be right on top of them for this to work. He was able to calculate, which was really cool, that the energy of these quantized states equals minus RhC over n squared. Now, h is Planck's constant. We saw that already. C is the speed of light. We saw that. R is what they call the Rydberg constant. It's this number right here. We're going to talk about the Rydberg constant, but it's not a number that you have to have at the ready. We're not going to use it that much. But most importantly for us, n is just a whole number, 1, 2, 3, 4, 5, 6, etc., never zero, never a fraction. N is called the quantum number, and these are the quanta states that the electron can be in. So you could have an electron at n equals 1. You could have an electron at n equals 2, but you couldn't have an electron at n of 1.5. You have to have a whole number, and he called them quantum numbers, and that's going to follow us into the next discussion. So this is pretty cool. All right, here's the Rydberg constant. You don't have to know that. We're going to use it a little bit, but you don't have to know it. There's Planck's constant and the speed of light, and those numbers we will use a lot, and I do encourage you to know those. But also then here's this quantum number, 1, 2, 3, 4. And that's really interesting. Now, in current quantum mechanic theory, which has gone way beyond Bohr, these things are still there, all right? It's a little bit different variation of them, but Bohr was actually ahead of his time. He actually got onto something kind of accidentally, to be honest, which was pretty important. So Bohr's model does have application even up to this day, which is really neat. But the thing is, he just kind of pulled this stuff out of thin air and nobody understood where it comes from. But it had some really cool results. And those sharp line spectra for hydrogen, the 4 lines, and the helium, and the fingerprints that astronomers use, he was able to explain atomic spectra for the first time. And no one had been able to do that up until Bohr. Here's an example of what I mean, what Bohr's model was all about. Now, in the Bohr model, all right, there was the nucleus. That's the big positive. And then there was this 1, 2, 3, 4. And if you remember from the previous equation, or down here at the bottom, there's a 1 over n squared dependence. And mathematically what that means is that the gap from n to 1 to 2, pretty big, but then the gap from 2 to 3 is a bit smaller, and 3 to 4 is even smaller than 2 to 3, and 4 to 5 would be smaller yet, etc., etc., etc. So what Bohr postulated here is that electrons would start at the ground state. He called that n equals 1. And initially they would absorb some energy and they would go to a higher state, let's say n equals 2. That's an endothermic process. They have to absorb energy to make that happen. But after a while, the electrons would get tired. They get homesick, if you will, and they would go from a higher end state down to a lower end state. That process is exothermic. Energy would be given off as you get closer to the nucleus. So the sharp line spectra came about because electrons initially were shot up to a higher n value. And then after a while, they would come back down from the higher n to the lower n. This is an energy axis, this y-axis right here. And you can calculate, like we're going to do here in a little bit, the energy going from 2 to 1. And that energy can be related back to wavelength, E equals hc over lambda. Oh, it's all coming together. But anyway, Bohr was the first person to figure this out.
According to the Bohr model, when a hydrogen atom receives energy, its electron leaps from a low-energy orbit to a higher one, forming an excited state. As the atom loses energy, the electron jumps back to a lower-energy orbit, releasing light as it goes. When gaining energy, the orbit to which the electron jumps depends on the amount of energy involved. When the electron occupies the lowest energy orbit possible, the atom is said to be in the ground state.
So in that little animation, you saw the electron at n equals 1 being excited. All right, maybe it was heated up. Who knows? Gamma rays from another star exploding. I don't know. Whatever. Something. It absorbed some energy. It went from a lower n to a higher n. That's going to be endothermic. It takes energy to have that happen. However, after a while, it says, man, I want to go back home. So it goes from the higher n to the lower n. That's going to be an exothermic transition. Energy is given off, and those energies being given off are where the sharp line spectra comes from. And again, Bohr was the first person to figure that out, and it's pretty cool. Let's calculate the change in energy, delta E, for a mole of electrons, quote unquote, falling from a higher n, n equals 2, down to a lower n, n equals 1, all right? And it's a mole of electrons too. Now, I'm going to use the symbol capital L for Avogadro's number, which is what happens sometimes. Now, delta E, like the delta temperature we saw in the last section, final minus initial. So at the end, the electron's going to be at n equals 1, and initially, the electron's going to be at n equals 2. Now, minus RHCl, those are all constants, and they're the same for both final and initial. So if you pull those out, you have 1 over the n final squared minus 1 over the n initial squared. All right? So the final state is 1. The initial state was 2 squared. It's like 1 minus 1/4 or 3/4. So if you take negative 3/4 times RHCl, and I encourage you to do this yourself. Go ahead and do it in your calculator right now. Here's R, that's the weird one. H, 6.626 times 10 to the minus 34. C, speed of light, 2.998 times 10 to the 8th. Avogadro's, 6.022 times 10 to the 23rd. And I threw in here another one too. I also threw joules to kilojoules. There's 1,000 joules and a kilojoules. But if you've done this right, negative 984 kilojoules. And that is an exothermic transition. That means that energy is given off going from n equals 2 to n equals 1. Pretty cool. What is the frequency and wavelength of the photons emitted by the 2-to-1 transition? And again, we saw in the last slide that the delta E is 984. But before we go there, I want to talk about the upper picture. To get the electron to the n equals 2, it had to absorb energy to go from the n equals 1 to n equals 2. We saw that it's negative 984 kilojoules to go to 2 to 1. That's exothermic. And like a lot of things in thermodynamics, the opposite process, i.e. going from 1 to 2, is going to be equal but opposite in sign. So it's going to take positive 984 kilojoules to go from 1 to 2. Going from 1 to 2 is called absorption, and absorption spectroscopy is a big part of science. In biology and chemistry, we use Spec 21s and things like that. They are absorbance spectrometers. They measure the energy absorbed, and that's a really cool feature. And a lot of times in programs like CSI, they will use absorbance to figure out that, oh, there's the blood and stuff, but that's neither here nor there. In this section, we're mostly talking about the exothermic version of that endothermic process. So absorbance is endothermic. Emission spectrum, which is what we're talking about, are exothermic. Energy is given off. So it's from higher end to lower end. Absorbance is lower end to higher end. Emission spectrum, which is what we're talking about now, and that's what the sharp line spectra are, higher end to lower end. So anyway, back to your regular scheduled programming. The energy was negative 984 kilojoules per mole. Let's figure out the frequency and wavelength of the photons. Now, what we have to do is we have to get it down to joules per photon in order to go to wavelength and frequency. So we're going to turn kilojoules to joules. We're going to use Avogadro's to go from joules per mole to joules per photon. And then finally, we'll use E equals h nu or E equals hc over lambda to figure out the frequency and the wavelength. This first part here, we're basically turning quickly the energy into frequency. I turned the kilojoules per mole into joules per mole by multiplying by 10 to the third. This is the energy. I'm dividing it by Planck's constant and Avogadro's number. And if you do that, you will get directly the frequency. All right. Now, frequency, like we talked about earlier, is usually waves per second. And technically, on this one, you're going to get a negative wave frequency, all right? And you can have frequency going positive one direction, negative in the other, but the convention is to always have positive frequencies and positive wavelengths whenever possible. So if you reported negative 2.47 times 10 to the 15th, it would be okay, but the convention is to always use positive frequencies and positive wavelengths unless you're doing in other ones. But anyway, 2.47 7 times 10 to the 15th is the frequency of this particular transition. And if you want to figure out wavelength, wavelength equals speed of light divided by frequency. I turned the meters answer into nanometers, and it came out to be 122 nanometers. And this 122 nanometers was almost exactly in agreement with the experiment from the sharp line spectra. Bohr nailed it, and that was a true feat to his skill that he was able to do that. 122 nanometers is in the ultraviolet spectrum. It's not one of the lines that I showed you earlier, but it is one of the transitions, and that's really cool. At the bottom there, I've got the note again. Absorbance is endothermic and emission is exothermic, but they are equal but opposite in sign from each other. Which diagram, A or B, represents an emission line? And the answers are, of course, A, B, both diagrams, or neither diagram. Now, emission is always an exothermic emission line. All right, it's an exothermic process. And the y-axis on both of these graphs is energy. All right. So if you have an exothermic process, the beginning state has to be higher energy than the lower state. Or you can think about the electron as falling down, quote unquote, closer to the nucleus. The nucleus would be kind of like down here right now. So on B, you're getting away from the nucleus. You're going to have to add energy to get away from it. On the other hand, in A, the electron's getting closer to it. That's going to be giving off some energy. So definitely A is the emission line, all right? You go from a higher N to a lower N. And on A, you're going from 4 to 2, so you're getting closer to the nucleus. Again, B would be an absorbance line. You're going from 1 to 4, from a lower end to a higher end, and that's just going to take some energy. Absorbance and emission are both used a lot and stuff, all right? And there are ways to do all of these kind of things. The sample will absorb some wavelengths of light, causing dark lines in the spectra, and that's where a lot of these absorbance things will come from. So you can see down here in the bottom, here are some absorbance spectrums for different pieces. On the left-hand side, here's the absorbance spectrum for hydrogen, and you can see there's kind of like 1, 2, 3, and arguably 4 lines, 4 black lines. Those are the 4 hydrogen lines, but they're being absorbed. They're not emitted, which is what we saw earlier. So absorbance is a very cool technique, and there's lots of cool things you can do. You'll learn more about absorbance spectra probably in organic chemistry more so than here, but it's got a lot of neat uses, and they're both really cool. Emission is fun because, you know, the lights bulbs overhead right now are basically emission sources. Anytime you have light, a flashlight, whatever, it's an emission spectrum. That's what's causing the light. So it's kind of fun to talk about emission, but it also makes sense in terms of sharp line spectra, blah, blah, blah. Here are the different lines for hydrogen. Now, here's the N value on the left, 1, 2, 3, 4, 5, 6, etc., and they go up to 8, all right? And all of the transitions that end at N equals 1, all right, we don't see with our eyes. Those are actually more like ultraviolet lines, all right, and they're very, very hard to see. But the important part for us here is that all the lines that end at N equals 1 started with a higher transition. So these numbers right here are like the minus RHC numbers on the left-hand sides, and you can use the difference between those to find the energies. Lyman was the first person to look at those lines, and they were the ultraviolet lines, and those are cool. Paschen on the far right looked at the infrared lines, and that's cool. But Balmer's lines, which we talked about earlier, all the Balmer lines start at higher N and end up at N equals 2. And this is where those 4 lines come from that I talked about earlier, all right? The smaller transition, the 3 to 2 transition, has a small, has a relatively large wavelength, but a small frequency, all right? So that's why it's red. On the other hand, the 6 to 2 transition has a relatively short wavelength, but more energy associated with with it. So you're seeing all the kind of things right now. So the Balmer series for hydrogen, they all end at an n low, if you will, of 2. They start at higher n and go down to lower n. Sometimes people think about this as a type of a ladder, all right? And under the ladder is the nucleus. I'll just put a positive down there. This would be like 1, 2, 3, 4. All of the Balmer lines stop at the second step, all right? None of them go down to the first step. The problem with this ladder, though, is that as we saw, there's this 1 over n squared dependence. So really n equals 1 to n equals 2 is the bigger gap. N equals 3 is closer. N equals 4, n equals 5. So the steps get closer as you go up. That's why the ladder isn't the perfect idea, but sometimes it's cool to visualize it. And most importantly is that Bohr nailed these numbers with his theory. Nobody knew where they came from at first, but he figured it out. Very, very cool. So Bohr's theory was fantastic. It rocked science, literally. He got a Nobel Prize. He was really, really cool. Everybody patted him on the back because nobody was able to figure out where those sharp line spectra were coming from. And he said, aha, from the electrons. However, like with anything, there were some problems. Bohr's theory worked perfectly for hydrogen and helium plus 1, single electron systems, all right? But once you start having helium with 2 electrons or carbon with 6 electrons, his theory didn't work out too well. Also, he introduced the idea of quantum levels kind of artificially. He said, this is how it's going to work, but he didn't really know why. So Bohr definitely was a step in the right direction, but he wasn't right. He wasn't perfectly right. Now, it is important to remember, though, that hydrogen and helium plus 1 work just as well today as they did back in Bohr's time. He really did a good job. And he started people thinking about this. And I think that was what was really important about Bohr. So Bohr is a hero of mine, definitely. But anyway, the next step then people started talking about, figuring out, was to actually develop quantum mechanics, or what it's sometimes called as wave mechanics.